Red Dwarf, the most common star in the universe, making up roughly 70% of all stars. Red dwarfs burn so slowly that the smallest ones will outlive the current age of the universe many times over. They are dim, cool, and small, rarely more than half the mass of the Sun. None are visible to the naked eye, even though the nearest star to our solar system, Proxima Centauri, is one. Yellow dwarf, the category the Sun belongs to, though the name is misleading. Yellow dwarfs appear white from space. They sit in the middle of the stellar size range, burning steadily for around 10 billion years. The Sun is roughly halfway through its lifespan. Yellow dwarfs are less common than red dwarfs, but produce stable, long-lasting conditions that make them strong candidates for hosting life. Orange dwarf. Slightly cooler and dimmer than the Sun, orange dwarfs burn for 15 to 30 billion years, far outlasting yellow dwarfs. They are considered promising stars for hosting life because they are stable, long-lived, and still warm enough for liquid water to exist on nearby planets. Alpha Centauri b is one, just over 4 light-years away. Blue giant. Far hotter and more massive than the Sun, blue giants burn through their fuel in tens of millions of years, rather than billions. They are among the brightest objects in the sky despite their rarity. Rigel, in the constellation Orion, is one. Because they live short lives, they are found near the star-forming regions where they were born, never drifting far from their origin. Brown dwarf. Not quite a star, not quite a planet. Brown dwarfs form the way stars do, from collapsing clouds of gas and dust, but they never accumulate enough mass to sustain hydrogen fusion in their cores. The threshold is roughly 80 times the mass of Jupiter. Below that, the object glows faintly from residual heat and slowly cools over billions of years. They are difficult to detect because they emit almost no visible light. Protostar, the earliest stage of stellar life before a star has begun nuclear fusion. A protostar forms when a region of gas and dust collapses under its own gravity, heating as it compresses. This phase can last hundreds of thousands of years. The young star, called a T Tauri star at this stage, blows powerful winds that clear the surrounding disk of material. What remains of that disk can form planets. Flare star, a magnetically active red dwarf that periodically releases enormous flares from its surface. These flares can be many times more energetic than anything the Sun produces, briefly outshining the star's normal output by a significant fraction. For any planet in the habitable zone of a flare star, the radiation bursts would be intense enough to strip away the atmosphere over geological time. Proxima Centauri, the closest star to Earth, is one. Red giant. What a Sun-like star becomes when it exhausts the hydrogen in its core. The outer layers expand enormously, sometimes swallowing nearby planets. The Sun will become a red giant in roughly 5 billion years, expanding to engulf Mercury and Venus and possibly Earth. Red giants are cool on the surface despite their size, which gives them their reddish color. Red supergiant, the largest stars by volume. Betelgeuse, one of the brightest stars visible from Earth, is a red supergiant so large that if placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Red supergiants are the evolved form of the most massive stars and have lifespans of only a few million years. They end in supernovae. Subgiant, a star in transition between the main sequence and the red giant phase. As the hydrogen in its core runs out, the core contracts and the outer layers begin to expand, but not yet dramatically. The Sun will pass through this stage roughly 1 billion years before becoming a full red giant. Subgiants are slightly larger and more luminous than their main sequence counterparts, but have not yet undergone the runaway expansion that defines a true giant. Carbon star, a late-stage giant that has dredged carbon from its nuclear burning core up to its outer layers through repeated thermal pulses. The excess carbon absorbs blue light, giving carbon stars a deep orange or red color, some of the most vivid in the sky. They shed carbon-rich material into surrounding space, seeding the interstellar medium with the building blocks needed for rocky planets and organic chemistry. Cepheid Variable, a star that pulsates in size and brightness in a regular, predictable cycle, expanding and contracting over days or weeks. Astronomer Henrietta Leavitt discovered in 1908 that the period of pulsation directly indicates the star's true luminosity. By comparing that to its apparent brightness from Earth, the distance can be calculated precisely. Cepheids became the first reliable tool for measuring distances across the galaxy and later to other galaxies, which is how Edwin Hubble confirmed that the universe extends far beyond the Milky Way. Wolf-Rayet Star, a massive star that has blown off its entire outer hydrogen envelope, exposing the hot fusing interior directly to space. The stellar wind from a Wolf-Rayet star is so powerful that it sheds material at rates many times greater than the Sun's total mass output. The ejected gas forms glowing shells of nebulosity around the star. Wolf-Rayet stars are direct precursors to supernovae, and in the most massive cases, to gamma-ray bursts at the moment of collapse. Luminous Blue Variable, an unstable massive star near the upper limit of possible stellar mass, prone to violent episodic eruptions that temporarily increase its brightness enormously. Eta Carinae is the most studied example. In 1843, it became the second brightest star in the sky for a decade without exploding, releasing as much energy in those years as most stars emit across their entire lifetimes. It is expected to explode as a hypernova at some point, though when is unknown. Hypergiant, the most massive and luminous stars known, R136A1, in the Large Magellanic Cloud, has a mass estimated at more than 200 times that of the Sun, and a luminosity roughly 8 million times greater. Hypergiants sit at or beyond the theoretical limit where radiation pressure from within begins to overcome gravity. They lose mass continuously at extreme rates and have lifespans of only a few million years before ending in catastrophic supernovae or direct collapse. White dwarf, the remnant left behind when a sun-like star exhausts its fuel and sheds its outer layers. A white dwarf is roughly the size of Earth, but contains nearly the full mass of the original star. It is so dense that a teaspoon of its material would weigh several tons. White dwarfs cool and dim over trillions of years, eventually fading into dark remnants called black dwarfs, though the universe is not yet old enough for any to exist. Neutron Star, what remains after a massive star explodes in a supernova and its core collapses. The collapse is so extreme that protons and electrons merge into neutrons, packing a mass greater than the Sun into a sphere roughly 20 kilometers across. Neutron stars are the densest objects in the universe that are not black holes. A single sugar cube of neutron star material would weigh around 1 billion tons. Pulsar, a rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As it spins, those beams sweep through space like a lighthouse, producing regular pulses detectable across the galaxy. Some pulsars rotate hundreds of times per second. Their timing is so precise that they were initially suspected to be artificial signals when first discovered in 1967. Magnetar, a neutron star with an exceptionally powerful magnetic field, roughly 1,000 times stronger than an ordinary neutron star and quadrillions of times stronger than Earth's. Magnetars occasionally release bursts of energy so intense they can be detected from across the galaxy. A magnetar within a few light years of Earth would strip away the ozone layer. Only about 30 have been confirmed. Blue Straggler, a star found in old clusters that appears far younger and hotter than it should, given that all stars in the cluster formed at the same time. By rights, it should have exhausted its fuel and died long ago. The leading explanation is that it stole mass from a companion star or formed from the direct collision and merger of two older stars, effectively resetting its clock. Blue stragglers are one of the clearest examples of stellar rejuvenation, or the appearance of it. Stellar black hole, the endpoint of the most massive stars. When a star with more than roughly 25 times the mass of the Sun collapses, even the pressure of tightly packed neutrons cannot halt the implosion, and the core becomes a black hole. Stellar black holes range from a few to several dozen solar masses. They are invisible directly but detectable through their gravitational pull on companion stars, and the X-rays emitted by surrounding matter falling inward. Thanks for watching. If you enjoyed this video, please remember to like and subscribe for more content like this.